You know, we talk about artificial intelligence constantly these days, but how often do we actually stop to visualize the real architecture under the hood? Well, today we're going to completely demystify the AI backend. We'll do this by mapping its invisible digital mechanisms directly to something you're probably already pretty familiar with, the working mechanics of the human mind.
Here's our roadmap for decoding these concepts today. 1. Meet the AI brain. 2. The neural network backend. 3. Training versus inference. 4. Decoding language with transformers. And 5. Fine-tuning the machine mind.
Before we jump into the actual architecture, I want you to just pause and ask yourself, what does a machine's mind actually look like? When you type a prompt into a chat window, or say ask your phone to identify a song playing in the background, you aren't just querying some simple static database. You're actually engaging with an invisible architecture, a literal digital brain. So how exactly is this digital brain structured?
Let's start with Section 1, Meet the AI brain.
It really helps to think of AI as a series of nested layers, kind of like Russian dolls. The outermost layer is the broad concept of artificial intelligence, the whole shebang of mimicking human thought. Inside that sits machine learning, which is where systems actually learn patterns from data rather than relying on explicit, rigid programming. But if we zoom all the way down to the absolute core, we find deep learning. This is the true heavy lifter of the modern backend. It uses multi-layered networks to handle incredibly complex inputs, things like images, speech, and just vast amounts of human language.
Moving right along to Section 2, the neural network backend.
At the heart of that deep learning core are neural networks. These are literally computational models inspired directly by how our own biological brains operate. They're specifically designed to recognize intricate patterns and solve really complex problems. Just like human neurons pass electrical signals to one another to form a coherent thought, artificial neural networks pass data through layers of digital nodes to eventually reach a logical conclusion.
Picture it like this. It's basically a massive team of microscopic brains. Every abstract thought or highly complex decision is rapidly broken down into a cascading series of binary yes and no questions. Thousands, sometimes millions, of these microscopic nodes work together in a fraction of a second, combining their tiny binary decisions to ultimately solve a massively complex problem.
So, you might be wondering, how do these nodes actually know which path to take? Well, they rely on hyperparameters and parameters. Think of hyperparameters as the system's innate instincts. They are the rigid, established rules for whatever the task is. Parameters, on the other hand, are much more like learned memories. They're the unique preferences derived purely from the AI's past experiences and data crunching.
Just to wrap your head around the sheer staggering scale of this for a second, 175 billion. That was the estimated number of parameters within the GPT-3 neural network. That represents 175 billion individual learned memories and preferences that help the network evaluate its internal connections to give you a cohesive answer. And get this, the modern models we're using today, they are significantly larger than that.
Which brings us to Section 3, Training versus Inference.
Let's walk through the AI life cycle. Step 1, collect data. Step 2, train model. Step 3, test and refine. And Step 4, make predictions. Training an AI is surprisingly similar to a human learning how to ride a bike. You don't learn to ride by reading a textbook, right? You learn through repetitive practice, falling down, getting back up, and adjusting your balance. The AI does the exact same thing. It practices on millions of data points over and over until it successfully finds the right patterns.
I absolutely love this quote from Sherlock Holmes because it perfectly captures the transition here. When the AI is in the training phase, you can think of it kind of like Dr. Watson. It's simply observing vast amounts of data and learning how the world works. But once that training is finally done, the model enters the inference stage. Now, it becomes Sherlock Holmes. It takes everything it has learned to draw rapid, highly accurate deductions based on brand new, unseen clues.
And here is the absolutely crucial distinction to keep in mind. During inference, the AI actually stops learning. Learning requires immense computing power. So by essentially freezing its neural pathways after training, the AI can deliver rapid, highly efficient, and consistent answers to your prompts without breaking a sweat.
Okay, so we understand the broad mechanics now. But it begs the question, how does this highly mathematical AI brain actually understand something as fluid, messy, and nuanced as human language?
Let's unpack that in Section 4, Decoding Language with Transformers.
Humans use language, right? Machines use geometry. The machine mind doesn't actually read whole words the way we do. Instead, it uses tokens. Tokens are these small chunks of text or data that get encoded as mathematical vectors. The AI basically plots these vectors in a massive, multidimensional space. Words that have similar meanings end up grouped closer together in this mathematical space. This allows the AI to literally calculate the geometric relationships between our human concepts.
To give you a concrete sense of this, a single token averages just 4 characters. That means before the digital brain even really looks at your prompt, it has already chopped your complex, flowing sentences down into these tiny 4-character mathematical chunks.
Now, in the past, AI used what we called recurrent neural networks. These read text sequentially from left to right, exactly like we read a book. The problem was, the AI often forgot the beginning of a really long sentence by the time it reached the end. Transformers completely solved this using an architecture called self-attention. This was a real game changer. It allows the AI to look at every single word in an entire sentence simultaneously. By paying attention to everything all at once, it grasps the full context flawlessly. You can really think of natural language processing like a giant childhood finish-the-sentence game. If we input the prompt, Zapier is, the AI immediately analyzes the tokens, references its vast training data, and predicts the most mathematically probable next tokens. It might output an online automation tool that helps connect, or it might slightly vary it to an online automation tool that connects your apps. It isn't just regurgitating a stock pre-written answer, it's literally building a coherent sentence on the fly based purely on probabilities. Let's wrap up with Section 5, Fine-Tuning the Machine Mind.
A raw AI predicting words based on everything it read on the entire internet? Yeah, that would be absolute chaos. So, developers shape it using 2 main techniques. First is RLHF, or reinforcement learning from human feedback. This is where human testers rank the AI's answers, effectively teaching the digital brain a reward system to steer away from unhelpful or harmful responses. Second is COT, or chain of thought reasoning. This teaches the AI to literally pause and think logically, forcing it to break down complex math or logic puzzles step by step before rushing to spit out an answer.
Still, the system definitely has its cognitive limits. Because it's fundamentally a pattern matcher at its core, it suffers from hallucinations, confidently inventing facts just to complete a text pattern. It also reflects whatever historical flaws and human biases exist within its training data. And finally, there's the black box problem. Because decisions are distributed across billions of different parameters, it's often impossible for humans to trace exactly why the AI made a specific decision. Honestly, sometimes even the developers who built the model cannot trace the actual step-by-step thoughts of this machine mind. But despite those current limitations, we are rapidly moving way beyond the simple chatbot. The future of AI relies on taking these incredibly powerful transformer models, securely connecting them to trusted enterprise data, and deploying them as autonomous agents. This means they won't just sit there and generate text. The mind will actually start acting, executing complex, multi-step workflows in the real world completely on our behalf. So I'll leave you with this. If these digital minds are already learning to infer, reason, and act based on our data, what exactly happens when they start generating their own data and teaching themselves? It is an absolutely fascinating and perhaps slightly intimidating frontier. Thank you so much for joining me on this explainer today. Until next time, keep questioning the invisible architecture operating right behind your screen.